Hi, I'm Natalie, and I'm here with Christina, and this is our video presentation of our project, Predicting Yelp Ratings from Text Reviews. Yelp allows users to comment, rate, and review restaurants and experiences, with most users rating their experience from 1 to 5 stars. However, after reading some of these Yelp reviews, we found that these reviews are extremely subjective, with some users providing harsher reviews than what would be standard. User ratings can also be swayed by personal preferences, which varies from user to user, with certain users weighing certain aspects like service more highly than others who might focus on food quality. Therefore, there is some utility in providing Yelp-suggested standardized ratings. Our goal is to generate a Yelp-suggested rating by analyzing the sentiment of user-provided reviews and calculating a numerical rating that's reflective of that review. There's been some past related work regarding the Yelp dataset. There are 2 papers published in 2014 which focus on statistical-based approaches. A paper published in 2016 looked at reducing computational time for this large dataset by implementing a MapReduce implementation. And another paper in 2017 analyzed the overall corpus to identify some interesting features that they then used to do a prediction on the Yelp dataset.
So we use the Yelp dataset, which is a curated dataset of reviews provided by Yelp. This data comprises of approximately 5 million separate reviews. So each entry has the text-based review, the star rating, the metadata including the restaurant name and the number of funny, useful, and cool votes from users. So due to computational constraints, we will be training on the first 10% of the data, which is approximately 500,000 reviews. So our first method was vanilla logistic regression. So this, we started by extracting the text-based review. We then removed punctuation and new lines and changed the review to lowercase. After that, we implemented a bag of words approach, which averaged the embedding of every word in the review. So our main question in method 1 was whether the size of embedding mattered. We looked at 50-dimensional, 100-dimensional, 200-dimensional, and 500-dimensional glove vectors. We then ran our bag of words vector as our feature vector in logistic regression. We measured the error using 2 methods. The first of these methods was the average error, where we take the average difference between the predicted rating and the gold standard rating. We also reported a confusion matrix to understand where the model does well and where it had shortcomings.
Here we plot the mean error for 3 different embedding sizes. For all embedding sizes, the model far exceeds the baseline, which was assigned by assigning all reviews to have a rating of 3, and the baseline kind of gave a mean error of about 1.5. We also observed that there's a definite trend with regard to embedding size, where larger embedding sizes give lower training and validation error. Our best model was created using 300-dimensional glove vectors. Thus, in a bag of words approach, more information about words is beneficial in classification, and having more dimensions does not lead to overfitting. We obtain an equivalent test set accuracy of about 0.5 for 300-dimensional embedding sizes. We then look at the confusion matrix, and we see that the model does very well in predicting 1-star review and 5-star reviews. 90% of 5-star reviews are classified correctly, and 78% of 1-star reviews are classified correctly. However, the prediction accuracy drops below 50% for middle-range reviews, and thus we conclude one of 2 things. First, it's possible that our model is failing to capture some of the nuances of the reviews. It's also possible that the reviews are very subjective, where some users are harsher than others. We then look at some of the big mistakes that the model made, where it completely misclassified the review as being bad when it was actually good, or vice versa. First, we look at the first review, and we see that this review has many positive words. And this, in fact, in the review relates to a different restaurant, not the restaurant which the user is reviewing. Thus, we see in a bag of words approach, this type of information is lost because we're averaging the words in the review. And this leads to a prediction of 5 when the true review has 2 stars. We also look at the second example and we notice a similar thing. The review has many positive words, which in this case relates to an imaginary pie, not the pie that the restaurant was serving. And this leads to a prediction of 5 when the true review only has 2 stars.
So we then hypothesized that perhaps the most important sentences in a review were the first and the last sentence, where a person will give their overarching opinion of the restaurant. Because of this, we tried another approach where we use a bag of words approach on the first and last sentence of the review. We then run this through logistic regression. We used 300-dimensional glove vectors because we found in the first experiments that larger word embeddings benefited prediction accuracy. Unfortunately, we found that this did not work. Our training, validation, and test error are much higher, and from this we concluded that more information in prediction is better. So, in conclusion, we are getting pretty good accuracy, especially in detecting the binary classification of good versus bad reviews. However, we are still missing positional and relational information.
Because of this, we think it's beneficial to train positional weights from a bag of words approach, where instead of just taking the first and last sentence, we use this as another feature that's trainable, and also might be useful to capture relationships between words through recurrent neural nets with attention.